Actual spacecraft.
Yes. Maybe he presses a button, or maybe this is projecting online very clearly, and
they can hear all of it.
Yeah.
Former creatine.
Oh,
3 postdocs from RIT, 1 grad student, and another grad student from RIT are all here now.
it's a great cohort. There's a strong RIT to Space Telescope pipeline, huh?
Yeah. Pretty much. And it seems until the very long time.
It's a blessing, really, because most of the time 5 minutes goes by in the blink of an eye, and I've got nothing done for the day. So,
It's all relative.
yeah, no, these moments where the moments drip and get longer, I really enjoy, actually. You cram more life in every second, you know.
So philosophical.
Yeah, yeah.
That's your bio. Philosopher and
Space philosopher. Sit down. Yeah. It is, I should talk for 45 minutes, is that it?
it's about 15 minutes. All right. Hello, everyone. Can you hear me okay? All right, we're going to get started. So today we're fortunate enough to have Professor Joel Leja here, who is the Dr. Kiko Miwa Ross Mid-Career Endowed Chair and Associate Professor in Astronomy and Astrophysics at Penn State University. He researches how galaxies like the Milky Way form over cosmic time using ground and space-based telescopes, large cosmic surveys, and supercomputers. He specializes in modeling observations of distant galaxies and in data-intensive methodologies applied to astrophysics. Joel received his PhD in astronomy from Yale University under Dr. Peter Van Dockum in 2016. He was an NSF Astronomy and Astrophysics postdoc fellow at the CFA with Dr. Charlie Conroy until 2020, and he was named a Clarivat highly cited researcher in both 2023 and 2024, meaning he is the top 1% of cited researchers in astrophysics. And he also was awarded the Yale University's Brewer Prize in 2019 for a PhD thesis of unusual merit. So let's hear what he has to say today.
Awesome. Well, thank you, Rebecca, for the lovely introduction, and thanks everyone for the great chats we've had today already. I'm here to talk to you about, again, but better, faster, and more physics. And so I think as astronomers or astronomy-interested folks, we're all used to being able to do better science with bigger telescopes. And we build a bigger telescope, we do more science, which is a very well-trod pathway. And for that reason, I do spend most of my time thinking about Webb, thinking about how distant galaxies evolve and what we could do better with the data. But in addition to this sort of breathless science at the edge of the universe, which I will definitely touch on, I also work on these new data-intensive methodologies. And that's what I'll be focusing on today more. And so we're still kind of learning how to do machine learning effectively and how to use it to do better science. But we've started building these next generation tools, and I really think it's going to completely change the way we ask scientific questions and change the kind of science questions we can ask. Okay, over the next 5 years even. I don't think anyone's prepared, and I don't think I'm prepared. That's why I think about it all the time. And so just to be clear, I'll give away some of the punchline ahead of time. 5 years ago, I was a postdoc at the CFA at Harvard, and things that took me millions of CPU hours on the supercomputing cluster there, now my postdocs can do in a couple hours on their laptop. Okay, the field is completely changing. It is becoming much, much faster. We have something like a factor of 1,000 to 100,000 speed up in the kind of computations we can do, and that's over a very short period of time. And so the speed increases are actually probably the most boring part of this. I think what's really cool is that faster computations and more efficient computations let us ask very different questions. That's what I hope to get to today. And so that's the plan That's where we're going. What kind of new science can we do with these methodologies? And you can maybe worry about whether it's robust or not. Okay, so let's dive right in. Let me restart this. And now we're diving right in, okay? Thank you for your patience. Good. I start most of my talks with this field. It is very rare that the person whose name is at the bottom of this image happens to be in the audience, so Bob Williams. But the Hubble Deep Field is one of the most influential pictures taken in astronomy, I think. And so this is galaxies at very great distances, a wide range of distances, and a deep field on the sky. And for many people, the first thing they want to know about this are distances. And we try to measure distances to these galaxies. But beyond distance, galaxies are kind of cosmic ecosystems. So understanding the evolution of galaxies, their formation and their evolution, yields rich information about the underlying physics. So we can measure things like the formation histories of these galaxies, their star formation histories, the total amount of mass locked up in their stars, their metallicities, their dust attenuation, and much more. And from that, we can extract all sorts of interesting fundamental physics about the universe. This has implications across a wide variety of fields. We do this for things like transient, to understand things like transient progenitors, cosmology, stellar evolution. Galaxies are cosmic ecosystems, and that makes them excellent laboratories for different types of science you can do. It also makes them difficult to understand because there is a lot of physics packed into small regions, and you need to kind of understand all of it at once to interpret an image, or worse, a spectrum. So what I think about a lot of the time is inferring the properties of these cosmic ecosystems and all the things inside of them by fitting their spectral energy distributions. And for me, that means taking absolutely beautiful galaxy data. Here, this is, of course, Andromeda. And turning all of these beautiful images, or spectra, into even more beautiful inferred parameters. And we're trying to measure things. Again, stellar mass, star formation history, nebular properties, dust content, chemical abundances, active black holes and their properties. That's the goal. So that's what I think about this map from data to inferences. Bayesian thinking has become more and more popular in this field, and for very good reason. As astronomers, we're studying very distant things. We get at best images or spectra of very, very complex ecosystems. So lots and lots of things control the light that comes out of these galaxies, and we don't really have very constraining data in the end. If you get a picture of a system with 100 billion stars, how much can you really learn about those stars? Even with lots of picture, even with a spectrum, it's hard. So that means this is kind of the sweet spot for Bayesian statistics, where you have lots of stuff you want to know, and your data doesn't really tell it to you. You can imagine a data-dominated or likelihood-dominated problem where it doesn't really matter how you write down the model, you always get out the answer because the data tell you so much. And you can imagine something that's more of a prior-dominated problem, where your data actually don't tell you anything. This is the realm for theorists. And for better or for worse, distant galaxies kind of fall in the sweet spot in the middle, where the data tell you some things, but you need the right models to interpret them properly. And that's why I think about this all the time, and that's why we use Bayesian statistics for this. You need to set up the problem correctly to get at a good answer. This is just a little example of that process here. This is Prospector. This is an open source Galaxy SED fitting code I spent a lot of my life thinking about and working on. And what I'm doing here is just adding more and more data points, starting from one band of photometry and going all the way out to a very well sampled far UV to far infrared SED. Okay? And then over here, we have a bunch of things that we're learning from the data. Things about the stars, things about the dust attenuation, the dust emission, things about the AGN. Okay? And so what I want you to take away from this is that you can see as we add more data, we converge towards the truth marked here in blue. And that's good, that's great. But maybe most importantly, even when we only have one data point, we have learned things about the parameters we want to know. And it turns out if you have one band of photometry, you know the mass of a galaxy to within 0.6 steps or so. A factor of 4, actually not that bad. So as long as your machinery works well, you can have one data point and 100 parameters, and you'll get back exactly what you know about that system. It may not be very much, but it's an honest representation of the truth. This works perfectly well as long as you have the right models. If you can write down exactly the physics you're trying to model, then you can throw it at whatever data you happen to have, and you get out honest, correct, true answers to the best of our ability. That's science. That's the goal, right? And so there's nothing about needing n parameters for n data points or something like this. And with Bayesian thinking and MCMC and these new fitting approaches, you can have one data point and infer hundreds of parameters. You just won't get a good answer, maybe. So the universe can be arbitrarily complex. As long as we can simulate the right physics, we're on a good path. Can we do that yet? Bayesian inference, my favorite tool. Powerful but dangerous. This old saying, I'll bring it up several times, all models are wrong, but some are useful. So are we good enough to be useful yet? What does useful mean? It means we create new knowledge. We learn something new about the universe. Not everything is right, but if it's right enough to learn something new for us, then we're on the right path. Well, we really have to understand our data to get there. We have to understand measurement uncertainties, instrumental effects, sky noise for those of us who are still on the ground. We also need to have reasonably accurate generative models. We need to be able to simulate the physics we want to learn fairly well and often fairly fast. And it needs to actually describe what we're trying to fit, otherwise we're going down the wrong path entirely. And if these things aren't true, you should be careful. I mean, you'll get an answer, but it won't be right. So we should always be asking these questions. Do we understand our data well? Are we applying the right physics? Do we have all the right physics? Are we on the right path? Are we creating more knowledge? Or are we maybe doing more harm than good with these kind of models? So, are we there yet? Can we study distant galaxies and get out good answers? Is my career worthwhile yet? I don't know. Let's find out. I'm going to talk a little bit about some of the mysteries of the early universe that's come out of Webb. And these are the things that keep me up at night. So these don't have answers yet, but we hope to generate those answers soon. This is one of the most exciting things I think that has come out of Webb, in my opinion. The second most exciting class of discoveries behind little red dots, which I will not talk about today. This is a bright quiescent galaxy at redshift 5, effectively, with a gigantic Balmer break. Right here. This was discovered in the Ruby survey. And we can go ahead and fit this galaxy. It's already a surprise to find a quiescent galaxy at redshift 5. No one would have predicted that 10 years ago, much less 30 years ago. But here we are. And it's a big one. Very bright. We have a beautiful spectrum. It's a very small thing. 500 parsec size, minuscule, a fraction of the Milky Way. Yet somehow, there are 100 billion solar masses of stars in this object. Very strange. So we can model its rest optical spectra and its photometry. We have that to very high precision from Webb, which is a beautiful instrument. We find a huge amount of stars. This is consistent with its dynamical mass, so we're not barking up the wrong tree here. So it's massive and it's early. And so the key question is, when did that mass form? And how quickly did it form? And so here, this is just the inferred star formation history. Age of the universe, 0 is the Big Bang. 1.2 billion years is when it was observed. And here I've drawn two lines, which are two plausible star formation histories for this object. We don't know which one is true. Both solutions are very weird. We have one metallicity. It's a solar metallicity solution. It's quenched at redshift 6, and it has an epsilon star formation history. The star formation efficiency, this is the percent of baryons that have turned into stars, that is 20%. To be clear, for the Milky Way, that number is about 5%. This thing has already been 4 times more efficient than the Milky Way at redshift 5, and it's done. It's turned off. Bizarre, right? This is the less weird solution. This is the blue one. The other fit, and this is about equally likely, it has about 20% solar metallicity. It forms at redshift 10 and is quenched by redshift 10, and it requires turning all of the baryons in the halo into stars. That is not a thing we do in galaxies. Galaxies are very messy eaters. This solution It's not in tension with lambda CDM. I don't think we can do that with galaxies. Our math is too rough. Our estimates are too order of magnitude. But it's a very uncomfortable thing, and that's always exciting. It means we're going to learn something new. And so this is my second most exciting discovery from Webb, these weird, massive dead things at the beginning of time, basically. Why are they so efficient, and why have they died? Preposterous, you might say. I would say that too, actually, a couple years ago. Or is it? These are popping up all over the sky, actually. There's a lot of them now. There are multiple independent teams. They have found these dead galaxies using Webb, typically. Very massive, greater than a billion solar masses at early times. The rest optical spectra all suggest formation and quenching at very high redshifts. They find very high star formation efficiencies. And here's a sample of them from the Excel survey. There's even more extreme objects at slightly lower redshifts that are even more unbelievable, honestly. And so this is a big puzzle. Why do these exist? I don't know yet. I have some answers, but I won't tell you too many of them today. If you have a good idea, let me know. I don't think we're changing lambda CDM, but it would make this easier. But I don't think we're doing that. We're something going on with the baryons. We'll learn it eventually. Good. Other mysteries of the early universe. There are several. There are many, actually. I'm just listing a few of my favorites. Here is a collection of spectra from the James Webb Space Telescope. This is from Harley Katz's paper 1 year ago. And all of these spectra share something unusual. It's a bit hard to see here, but there is a feature here. This is all an observed frame, so you can't really trace the correct wavelength. There's something called a Balmer jump here. Where at the Balmer break, well, normally we call it the Balmer break, around 3,800 angstroms or so. Usually, we have a lot of hydrogen absorbing photons. You get this break in the spectrum. Instead, we have a jump. It's going the other way. This isn't unseen. We see this all the time in H2 regions, where there are a ton of ionizing photons and a lot of gas. I had never seen one of these in an actual galaxy until Webb launched. I think they existed before. I just personally hadn't seen them. I'm still learning myself. But now they seem to be very, very common. This is weird. I'm not going to get into the physics, but in brief, having nebular continuum dominate the UV means we're producing a ton of ionizing photons. It's very efficient. Something in these galaxies is very, very efficient at pumping out ionizing photons. It's possible to do it with stars, but they're not at the level. Well, this is the debate. Can you do it with stars? Do you need something more exotic, like a top-heavy initial mass function, sort of ubiquitous AGN mixed into everything, some sort of exotic stellar models? It's not quite clear yet. It's a bit of a puzzle. Why are these things so common, and why are they so bright? Why is there so much nebular continuum? What's doing the ionizing? I don't know yet. This is something I think about a lot, too. Additionally, this is a little movie here made by a postdoc in my group, Nico Cleary. So here we're just showing this common diagnostic diagram. This is the BPT diagram. Normally this is used to separate AGN and stars, yellow and blue. And it works very well in the local universe. Here I'm just scanning through different gas metallicities and ionization parameters. And the point here is that in the local universe, at around solar metallicities, at lower ionization parameters, this does a beautiful job at separating AGN, active black holes, and stars. But when you get to low metallicities, at the beginning of this movie, or high ionization parameters at the end of this movie, that separation disappears.
So where's the emission coming from for your stars?
The stars are a wide range of stellar populations of different ages, metallicities, and stellar population synthesis models.
The stars, the cells are not giving the emission lines. Where are they coming from?
Oh, this is from cloudy. Yes. The gas is ionized by the stars, and then yeah, it comes out.
Region, right?
It's an H2 region. Yeah. Yes. Our standard assumptions don't really separate stars and AGN in the early universe. Maybe you'll argue they never did, and the nebular physics is more complicated than what we put into these models, and there's some merit to that argument. But there's no question that it doesn't work at early times. We need new, better tools. One more puzzle I'll point out. We found massive quenched galaxies at early times. That might have been expected, maybe, if you believe the SDSS results at redshift 0, which Well, now I definitely do. But what we didn't expect to find is very low mass quenched galaxies. That's been a real surprise. So little tiny dinky little things like the LMC or the SMC that have these Balmer breaks at redshift 7, 6, 5. And so what it implies is that we have the cessation in star formation rate. And you could say, well, maybe we're all catching them at an early quenching phase, and I don't think that's accurate. I think the more common interpretation is that we have very bursty star formation. And we have a lot of star formation, a huge amount of feedback, blows out or heats the gas, things slow down for a while, and then they turn back on. It's kind of an elegant solution. It's kind of a disaster for people like me who do this modeling, though, because if we have bursty star formation, it kind of, every new burst totally obscures your history. You can no longer measure star formation rates very well, or masses very well, or anything very well. All you can tell is that things are bursting or not bursting. So it's important, I think, to measure things like the duty cycles and the time scales. And I think this will be very useful for feedback models and galaxy formation simulations, which all work in very different ways and predict very different effects here. So measuring this well would be great. Well, that's what I do. Right, I can recover star formation histories from SED modeling. So we can solve something like this by analyzing their SEDs, right? That's why I'm here. That's what they pay me for. I can do it, maybe. No. I want to show you a SED modeling experiment that was led by Cami Pacifici here. This was an amazing experiment. She got together people from all over the community who build these codes and run them. And she gave them all the same very high quality photometry and said, fit this SED, and we'll compare the outputs. This was, well, we found a lot of bugs. It was also a major exercise in diplomacy. But the outcome really, well, let me show you. Okay? So we have this experiments. We have these popular different SED fitting codes, something like 12 of them. They're all applied to identical, high quality, rest UV to ultraviolet space-based photometry, mostly Hubble. And this is what comes out. Oh, don't know what that was. Boop, boop, boop. There we go. Here I'm plotting the mass on the x-axis versus the star formation rate on the y-axis. These are all the different codes. Don't worry about the color coding. And I will just point out that each of these axes covers something like 3 or 4 orders of magnitude. This is the star-forming sequence. It is very fundamental to galaxy formation. Most of the stars in the universe form from galaxies on this sequence. And for the aficionados out there, you're maybe already worried, but if you stare at this, you start to see very, very, very different features from all these different codes. This line here is the same line in every plot. It's not a fit. It's just to guide your eyes. And you can see we have different locations of the star-forming main sequence. They move up and down by factors of 4 or 5, depending on which code you use. Okay? You have different amounts of scatter around that sequence. And you have different amounts of bursting or quenching experiences going up and down. You have different amounts of quiescent galaxies, and how dead they are changes from code to code. This so-called green valley, the area that a star-forming galaxy will go through from star-forming to quenching, changes. Some codes have a green valley, some codes don't have a green valley. It implies very different timescales for quenching. Basically, what you have here is something like 13 different models for galaxy formation. And maybe it's not quite that extreme, but it's not that far off either. So this was a very eye-opening experiment to me. Why? These are 13 very reasonable people. I am one of them, so I'm biased. But these people aren't making simple mistakes. These are good faith efforts to do really good science. We're all getting different answers. Why? What are we all missing? Fine, photometry are hard, right? They're just pictures. We can't do much with pictures. What about spectroscopy? And in fact, I'll one-up you. These are the best spectra of distant galaxies to date, in my opinion. They're not that distant, which is part of the game. Hey, these are something like 20-hour rest optical spectra on an 8-meter telescope, the VLT. This is the legacy survey. We have something that's like similar noise of 50 per angstrom at resolution of 3,500. That's great for people who do galaxies. Okay, 3,500, very good. These are fantastic spectra. They're just beautiful. These are zoom-ins around the Balmer break region. You see all these wonderful absorption lines here. And we should be able to learn a lot from these. No one can disagree with these data. They're so good, right? 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 Okay, here's the metallicity. These are 3 different codes this time. This is a smaller experiment, but these are for the aficionados, bagpipes, prospector, and a Lick index fitting thing from Anna Galazzi and collaborators. These are the inferred stellar metallicities from these beautiful continuum spectra compared between the 3 different codes. And we tried dozens of things to figure out why this looks like an almost pure scatter plot. And we're comparing definitions of solar metallicity. We spent hours in a very hot room puzzling over this. We still don't have a good answer. I have some theories. But the metallicity from even the best spectra that I've had the pleasure of fitting, not great. Fine. And here's the ages. The ages are a bit better. But I'll say I'm plotting the light-weighted age, which is the easy thing to measure. It's the age of the light that we see. It's not the mass-weighted age, which is what we care about. That is very bad. I don't show that to people. It's not the light. Why? Why is this so hard? Here's my theory. We just don't include enough physics. We just don't cram enough physics into these codes. Stellar populations are complicated, dust is complicated, gas is complicated, black holes are complicated. We can't cram it all into these codes. We can't do it yet. And many different physics are in play. You have to make approximations for this to be tractable. Those approximations create systematic uncertainties. That's the game. That's why it's hard. So again, all models are wrong, but some are useful, hopefully. And hopefully we can get to the point of them being useful. I'm going to play a little movie. Bring your popcorn. On the left here, this is a parameter that affects the galaxy SED, and on the right is the order of magnitude effect on the SED as determined by me personally. Let's go. This is the abbreviated list. This goes all the way down, right? I stopped here. There's no magnetic field. There's no cosmic rays. There's no orientation. There's nothing. This is a hard problem. That's why everyone's getting a different answer. They have different but reasonable approaches to all of these things. And the output is just a bit incoherent right now. What do we do? I think what we need to do is add more physics, add a lot more physics, and start getting reasonable answers out of this. We have something like 10 or 15 parameters. I think we need a lot more. We need at least a lot more to convince ourselves that we can get away with a lot less. And that's the thesis of this talk. Good. Well, maybe you accept that, maybe you don't, but we're diving right in. If you accept it, you might say, Joel, you can't do that. Current models already hit the computational limits. If you try to run Prospector, you know it's slow, and this is why. The problem is that high-dimensional models, if you want a 15-dimensional model, you want to put that on a grid, that scales exponentially in size. If you want a 15-dimensional model with 10 spacings in each variable, you need something like a Google data center to hold all of your models. So you can't go from 15 parameters to 20. You need to sort of harvest the sun or something for more data centers at that point. How do you get around it? Well, you can do this on-the-fly computation and generate models when you need them. But that's expensive. It's a compute-intensive task. I know this because I spent much of my postdoc moving around factors of 2 and optimizing to get an additional 40% out of combining these SSPs in smart ways. We kind of we're at the limit of the grid at this point. And so if you accept this, it takes something like several million CPU hours to analyze a typical deep field, to my level of precision. Why? Why is it so hard? What's driving the computational requirements? We start with observations. We do all the physics we need to generate a model. This is lightning fast. We can do about 20 models per second. Many graduate students have sacrificed their careers for this. I certainly sacrificed 5 years of my life for this. So this is pretty good. Well, you need about 1 million models per fit to get a good answer. And that leads you to about 15 hours per object. And that's about the limit. You can't really do much more. So how do we go faster? How do we cram more physics in here if we're already at this limit? Well, one answer is neural net emulators. And replace all of these complicated physical models with neural nets that are designed to exactly take in the inputs and replicate the outputs of these models. This reduces model generation time by an easy factor of 1,000. So maybe I wasted my time getting those factors of 40% out. To, well, 100 to 1,000, 10,000 on a GPU. If you have some NVIDIA stock, take note of this. And so this is just sort of coming online now in the past 5 years or so. It's enormously effective. How do we do this? We must lose something, right? We do lose something. Neural networks, as I promised, are very fast. This is my grad student, Elijah Matthews, who's dedicated a lot of his time to these. Here, this is the size of the network versus the execution time. And so it scales as about n squared. Up here, this dashed line, this is where our normal population synthesis models fall. And so most of our models are something like 100 to 1,000 to even 10,000 times faster than all of our physics calculations. So we're on a good path. We can make things faster. What's the trade-off? Well, we add errors to our models, right? We can only emulate to some precision. And so we spent a lot of time thinking about this. How much error can you tolerate? How much speed can we juice out of this while still getting the right answer? Well, we got a pretty good answer. As long as you're something like less than half of the typical observational error, you're in a good spot. You can get the right answers. So we found that magic number. We built these emulators. We go back and do all these tests. And we find that these neural networks give accurate inferences. And we can get things like mass and dust to very good accuracy. We just have to tune this trade-off between the model being wrong sometimes, which is very uncomfortable for some people, still me as well, and the model being much, much faster. And if you add enough error that you don't care about it, well, you're off to the races. One more thing that's maybe less obvious. Neural networks are also differentiable. You can do backpropagation. You can get out gradients. Why is that important? Well, with gradients, you can do this gradient-based sampling thing. That means you can be very, very efficient at proposing new points. And so not only are they faster, but they're also smarter, and you can add models in the right places. That turns out to be key. I'm not going to go into the details here. But in brief, if this is some likelihood space, this is our true solution. Normally, we kind of fumble there blindly. A random walk sampler, this is MCMC. This is what everyone runs normally. And we jump around blindly, sampling the likelihood until we get to the right answer. It's not very efficient, but it does work. But with a gradient-based sampler, you measure not just the height, but also the slope. You can very cleanly find the true solution. So these gradient-based samplers are very efficient at proposing good samples. So not only are we faster, but we need fewer models to get to the right answer, and that's key. That's what makes this all work. Okay, maybe I've convinced you we can speed things up. And so we can take this model out for a spin, and we did on Webb's first data. This is one of Webb's first deep fields. This is Dr. Bingji Wang, who was a former Johns Hopkins grad student who came to do a postdoc with me at Penn State. She did fantastic work. This is Abel 2744 from Webb. And so she did basically my entire postdoc on a modest compute allocation with brand new data from Webb. This was awesome. It just fit in a few days on a little cluster we have at Penn State. And she got 70,000 galaxies done, and this was great. We did a ton of science with this. The photometric redshifts performed shockingly well. We couldn't get photometric redshifts out of this before because it was so slow. Now it's very fast, and we found we can actually get very good competitive photometric redshifts, in some cases better than the previous state of the art, because we have this very nice high-dimensional space, which is very smooth. I'm not going to go into this. We used this to discover at the time the second and fourth most distant galaxies out to redshift 13 in this tiny little field. This was awesome. Hey, now we can take these high-dimensional models, we can spin them up everywhere, anywhere. Hey, they work fast. But that's boring, actually. It's very boring. We can do the same thing but faster. That's not very exciting. I want to talk to you mostly today about the completely new things we can do now that our models are so much faster. I'm going to talk about a few of these things. We don't need to build photometric catalogs anymore. We can fit every pixel as it is. We can forward model the imaging. We could forward model the PSF. We could fit models with tens of thousands of parameters and get out much better answers than we could possibly before. Not only can we get out better or faster answers, now we can get out better answers too by modeling the spatial resolution of galaxies, the spatial extent. Not only do we fit galaxies as their own unique little snowflakes, but we can also model the entire population of galaxies and get out uniquely different answers and better answers for some key problems that have plagued the field. I'll show one of those examples. And ultimately, this is my 5-year plan. 10 years. We want to learn or marginalize over all the relevant physics that we can. These models already exist. Hundreds of parameters in models of black holes, chemical evolution, stellar evolution, photoionization, nebular modeling. All these things exist. And if we can put them into these codes, we can do much better science. We just need to be able to handle the massive increase in parameterization. And I think we can at this point. Okay, so that's the plan. Let me show you some of the new things we can do. So normally, we treat stellar populations in distant galaxies as unresolved. You take a beautiful image of a galaxy, you draw a circle around it, you add up all the light, and you ignore the spatial complexity. But they aren't actually, not anymore, not with things like Webb or Hubble, and some people have done a lot of great work in analyzing resolved galaxies, including here. Abdurrauf here, working with Dan Coe, has spent a lot of time thinking about this and has done awesome work. And he shows you can fitting every pixel has key advantages. You can break these underlying degeneracies. You can kind of learn fundamentally new things about distant galaxies. A very simple one is that young stars tend to outshine old stars. And so if you add up all the light from a galaxy, you're dominated by the young stars. Well, if you have the spatial resolution, that's not true anymore. You can see the old stars directly. They're right here in the bulge. They just get dominated when you add up all the light. But the key challenge yet, this is the technical challenge that I don't think we've really addressed properly in the field yet, is that these pixels, you can't fit them as independent little galaxy SEDs. They're all correlated by the point spread function. They've been smeared. So you have to model regions of pixels. If you model one pixel, you also need to model tens of pixels around it because of the point spread function. So this is challenging. What it turns into is that you need to model something like 1,000 points at the same time, each with their own 15-parameter model. You quickly get up into this very high-dimensional model space. So this is a problem we've been tackling. We have this code which forward models an intrinsic distribution of stars, gas, and dust, smears it by the PSF, and then compares it to every type of photometry we have. And they have very different point spread functions, so you need to do this carefully. And this is just Hubble and Spitzer for you. So currently, we're in the early stages of this. We're just taking what works for unresolved galaxies and running it for resolved galaxies. It's not quite right, but it's a good place to start. I told you neural nets give free derivatives, so we get these hyper-efficient samplers, and that's really needed because fitting a 75 by 75 pixel image, well, it takes about a day on a GPU, and there's about 84,000 free parameters, right? Okay, this is where I lose some people in the audience. It works. It works surprisingly well, but there is a caveat, and it's a very juicy, interesting one, and we'll get to it in a second. And just to be clear, this would take about 110,000 core hours with classic fitting. So we've got something like a 5,000%, 5,000x speed up here. Does it work? Can I convince you this works? I have 85,000 free parameters. Do you believe me? Well, we'll get there. This is at the early stages, I think, and I'll tell you why it's hard. First, I will show you, this is a beautiful galaxy from Webb. It doesn't quite show up nicely here, but it's got a strong color gradient. It's observed in a ton of different filters. And if you fit it with this machinery, you get out these just absolutely gorgeous maps. Things like this is the mass map. This is the metallicity map. You see a strong metallicity gradient in the center going to the outside. So you can immediately see that approximating all of this as one system is not right. And we know that. We've always known that, right? So we get interesting spatial complexity from these fits. I promise better constraints from spatial resolution. I just want to show you in a perfect world where we know exactly that the models are right, we generate our own fate data and fit it, we can get mass, normally we get mass to within 20 or 50%. And with this approach, we can get mass to within about 5%, and it's well calibrated. The error bars are all right. So we can learn much better things, and this is just mass, the simplest thing to learn. We can learn a lot about the age, about the dust, about the metallicity, about the line emission, about the black holes. This is a very powerful technique. And We can take these fake data and show that if we don't account for the point spread function, we get the wrong answer, and by a lot, and we're really confident about that wrong answer. So this is just showing the z-score, so truth minus predicted divided by uncertainty. And the point is, if we use our full forward model, we get a very healthy z-score. Everything's within the right uncertainties. If we ignore the PSF, we get these big flaring wrong things. We get the wrong answer. So accounting for the point spread function turns out to be important. However, when you account for the point spread function, you introduce a deep degeneracy into your fits. Okay? And so before we take this and just run it on some GPU cluster across the entire sky soon, okay, we need to deal with this problem. More pixels, more problems. Here we have a 20-band Webb photometry, and we're fitting this beautiful spatially complex model with spatially complex observations with 5 different models. Okay. All of them reproduce the light distribution perfectly. Right? Beautiful chi-squared fit, right? But all these 5 models, they just make different assumptions about the small scale distribution of gas, dust, and stars. You have to try it out. This changes the answer substantially, right? By something like a factor of 4 in mass, by much larger factors in other parameters, and it does so very confidently. We still get these 1% uncertainties, even though our answers are different by factors of 4. And so the PSF smearing, it inherently allows many different types of solutions. And so you can go much farther here, but you need to have very good priors, or at least reasonable priors, on the small scale physics of dust and the dynamical mixing of stellar populations at different age and metallicity. So this has turned out to be a hard but fascinating problem, and I've talked to some of you about it today, and I have a lot of thoughts on this, and we're not going to go into any of them, we're going to move on. But this is an ongoing project that I think will have great merit. We can finally tackle it. And we have some new degeneracies introduced by the point spread function, which are quite deep, I would say. I think local galaxies might get us pretty far on this one. Good. Let's talk about something totally different. To understand the nebular emission in galaxies, often you have to run this beautiful code, Cloudy, which has been around for many, many years. And it does great work in modeling H2 regions and photoionization. You can predict emission lines from an input set of physics. It has often been said that I wish we could run Cloudy for every galaxy we see. But a single Cloudy evaluation takes something like 2 minutes. It's doing a lot of work, but it means you can't really loop it into an inference machine. So what we did was we ran Cloudy many, many, many times, and then we built a neural net emulator for it. And we did something specific here, which is normally you assume some specific ionizing source for this process. Here, we just wrote down an arbitrary 4-part power law with breaks at different ionization fronts for our ionizing source. And that means we can model any type of ionizing source in distant galaxies. So it's source agnostic. We can ionize the gas with anything we like. Black holes, normal stars, very weird stars. We also can free up a bunch of our model parameters. We don't have a mega Cloudy grid that we're working with because it's all wrapped into a nice tidy little neural net trained on Cloudy. So we can go a lot farther. This works surprisingly well. This has been done by my grad student, Leja Lee. She's now a postdoc at Northwestern. This is just showing Cloudy in action, or Q, which is an emulator for Cloudy. And here we give it a bunch of line luminosities. And it learns the true ionizing spectrum at the same time as varying the elemental abundances, the densities, and the ionization parameter. And so that movie will continue to play, but it does something like 130 lines and nebular continuum with less than 5% uncertainty. So we can wrap this in an inference loop. Each prediction takes something like 6 milliseconds, depending on your computer. That's something like 10,000 times faster than Cloudy, on which it was trained. That means we can wrap it in these inference loops and learn very different things about distant galaxies. So you can investigate mysterious ionizing sources. You can calibrate your models. You can learn about new models. And maybe there's ionizing sources that are harder and bluer than our normal stellar models. There seem to be. Or maybe your data aren't good enough to learn something new. You can also marginalize over the things you don't know. We don't know it, and we can marginalize over that properly and get out good answers for other things. Both are viable. This is just one example. We ran Q on the current redshift record holder, MOM Z14 at redshift 14.4. The Webb spectrum, well, it only goes out, it covers the rest far UV effectively. We get a few emission lines. We don't know what's ionizing the gas in this, the most distant galaxy. We don't have very good stellar models at these very unusual chemical abundances. So we run Q, and we find a lot of things that we don't normally put into our models. We find the supersolar nitrogen abundance. We find a very high gas density, much higher than the galaxies even nearby at the same time. And we find this incredibly efficient ionizing source with a large error bar. But this psi ion value, this production rate of ionizing photons, is just at the very edge of what our normal star models can do. You might imagine maybe something else is going on. Very massive stars, population 3 stars, unusual things, the first AGN, I don't know. But we wouldn't be able to find this without having a completely free ionizing spectrum from these neural net emulators. I'm getting close to the end of our time here, so I'm just going to quickly go through another question. What about ground-based spectra? There's lots of large-scale ground-based spectrograph surveys coming online right now. It's an honor to be living at the time where we're mapping large fractions of the observable universe in this way. I am a member of PFS, as are many people here actually, through institutional access. I'm going to give a brief story about PFS, tell you one more modeling trick, and then we'll end. This is one of the premier wide fields from the James Webb Space Telescope, Cosmos Webb. It's 255 hours of time on the Webb telescope, maps something like half a degree squared in a few broadband filters. It's a mega accomplishment. It's super cool. Here we're going to zoom out from Cosmos Webb. Cosmos Webb, all of this beautiful time invested into the sky is approximately half of one PFS pointing. PFS covers a huge area on the sky. It's sort of coming online this year, and we can find all sorts of rare things. Here, the red stars are the most massive galaxies, and you see they're distributed very rarely, such that we only catch a few, even with the PFS point of view. So we can find rare things very efficiently with PFS. It's going to be something like the SDSS at redshift 2. I'm super excited for this. I'm going to skip most of these things, but it's got a huge field of view. It takes 2,400 spectra at once. I labored away for many nights during my thesis to take 7 spectra with Mossfire on Keck, so 2,400 is still to me. And we have a great survey plan to sort of do the SDSS at redshift 2. And I'm not going to get into the details here. The spectra will be pretty dang good. Here I'm just modeling different ages for quiescent galaxies. And so we can ask things like, these maximally old galaxies we're finding at redshift 4, 5, 3. Can we still find them at redshift 1? And the answer is absolutely yes. These spectra look very different. So one of the things you can do is find these maximally old galaxies at lower redshift. Look for clues as to their formation, like funny stellar chemical abundances, formation histories, or maybe they're masked by new star-forming disks that are formed around them. Computational challenge, having millions of spectra. Well, I told you we built an emulator for photometry. We can do it for spectra as well. This is one of my students, Emily Burnham, who's able to build the spectral emulator, and we get something like 1% errors or less. These scale extremely efficiently as well on GPUs. So we can use a GPU to fit hundreds of galaxies at the same time, and we get factors of 100 to 1,000 speed up again. We can do spectra just as well as photometry. And we get this additional speed up in the gradients. So good. We're prepared to do the same thing again, but faster. But we can also do something new. And this is the last thing I'll tell you about. There is this problem that I mentioned at the beginning. Annoyingly, bursty star formation is nearly impossible to model in single objects because of outshining. The young stars are so much brighter than the old stars. And so this is a beautiful high solenoid Webb spectrum with a perfect model. Everything works as it says in our models because we generated the data. There's no model mismatch. It's perfect. We fit it perfectly to try and get out a bursty star formation history. The true star formation history is the dotted line here. And what we recover is the purple one with no bursts at all, despite fitting the data perfectly. Impossible. Well, this is a smoothly rising prior. We say the star formation rate shouldn't change that much. What if we tell it it's bursty? This is what happens if we tell it it's bursty. total disaster, okay? It just doesn't work. The information's not there. It's not there in one galaxy spectrum. It's really not. So this is kind of a disaster for people like me because we can't measure the star formation rate right. We can't measure the masses right. We can't measure the ages right, even if we know it's bursty. It's very frustrating. But there's a solution. Don't model one object. Model all of them at the same time. Right? And so we can do that now that we have very fast models. So it's impossible to measure these fluctuation timescales and frequencies in one object. It is solvable in populations. Here are different models for burstiness. One galaxy doing this is impossible to solve for, but these different models produce different distributions of observables. This makes this tractable suddenly. So we have a very simple model here. We can build an arbitrarily complex model by using something called the, well, instead of imagining one amplitude, one frequency, galaxies going up and down at the same rate, we can model an entire power spectrum of frequencies with amplitudes at different powers. We have different power spectra here, and it's a beautiful formalism, in part because the simulations all separate very, very nicely in this formalism. So if we can put an observed point on here, we can discriminate between all these different galaxy formation simulations very efficiently. These different power spectra produce different star formation histories, and most importantly, different observable distributions for the entire population of systems. So that's very powerful. I told you forward modeling one galaxy takes millions of models, so populations of galaxies might be intractable. We have this trick, simulation-based inference, where if you simulate a population on some supercomputer, you learn that simulation by training a machine learning algorithm on it. You can take distributions of noisy observables, pass it through this big square, which looks sort of like a black box, but don't look too closely, and you get out answers for your entire population of galaxies. So you can include things like measurement and Poisson counting noise. You can marginalize over nuisance parameters, like the distribution of stellar metallicities or dust. You can train it on a cluster and run it in seconds on a laptop. We can simulate whole galaxy populations in seconds now and get out good answers. So this is just one quick example. This is in prep for my grad student, Emily Burnham, who's done fantastic work on this project. It's very technically challenging, and we got it wrong 1,000 times before we got it right. But what we can show here is that if we take two leading formation simulations, the fire simulations and the illustrious galaxy formation simulations, this is a red line here on the plot for fire, and an orange line for illustrious, we can distinguish between them, the blue posterior, to pretty high accuracy. This is a simple 40-hour survey on near spec. So we can finally answer how bursty galaxies are quantitatively and well with this type of modeling. Here we find that fire is extremely bursty, and so we can only really measure timescales of about 20 million years before things go off the rails. This is as expected. This is physics working as we think. So we can do it. We can accurately recover this, and we can put it into a quantitative rigorous model, and we can marginalize over the things we don't know. These short-term fluctuations are very different in all these simulations. We can finally falsify the small-scale physics, the subgrid physics we put in to make these work. This is very nice. And we can also do much better SED fitting by knowing these bursts. We can put in the true burstiness prior, and we can get out good answers. And so I'm super excited about this. It was totally unsolvable before, and now because we can build these population models, we can answer these questions finally. So we have a few things next up, but we're really excited to apply this to web. So I just want to end on this note. This has been happening in the background the whole time. You've probably heard some of it. The time to fit a galaxy broadband SED using this on-the-fly approach. When I first started optimizing things, it was 100 core hours per object. After many years of work, we got it down to 20 core hours per object. Good work, right? Not really. Neural net emulators blew that out of the water pretty fast, down to about 10 core minutes per object. It took about a year or two for that. We have this GPU acceleration, these auto-differentiation models. We can get another factor of 10 out of that. And then, if you dare to try simulation-based inference, you can get something like 10 core seconds per object, blazingly fast. So we have this factor of 100,000 speed up in 5 to 6 years. we can do very different things and much more complex questions. We just need to parameterize the physics properly and put them in, and we are ready to go. I'm super excited to do it. So our last picture of Webb, I'll just leave up the takeaways from my talk here, and happy to take questions.
Thanks for showing us how a beautiful hammer can show a bunch of nails, right? I'm curious about something you didn't mention, though. So, it's a sort of well-known problem in Bayesian inference that with lots of complicated models, you can get much more multimodal posteriors. So do you find galaxies just are nice in that they give you single modes? Okay.
Yeah, you're pointing out probably the biggest worry I have, which is you add more parameters, you add more models, you get different solutions, and they're often widely separated from each other. These GPU or these gradient enhanced samplers are very good at exploring one mode. They're very bad at jumping between modes. So this is an ongoing problem. There's a few ways to solve it. One is just by starting your sampling in different locations. That's expensive. Another thing that we found, and this is maybe a better way forward, is simulation-based inference is actually amazing at finding different modes. It's super efficient. So that's the way I think it's going to work, is throw away the whole sampling framework and go to these machine learning models that just pop out samples all over the parameter space. Great at finding modes. The modes aren't always good. You have to test them. But yeah, that is the biggest problem, and there are ways to sort of kinetically force your way through it.
I think one limitation that we probably already run up against, or will soon, is the fact that, when you really make a detailed comparison between models and SEDs, the answer is going to depend eventually on aspects of the ISM that are very difficult to model and very difficult to parameterize. So, for example, even if you know the stellar population model perfectly, know exactly what the stars are doing, the distribution of dust and gas in the galaxy is going to make a difference. If you observe a galaxy from one direction and the same galaxy from another, they will have different SEDs. And part of the reason for that is the gross large-scale distribution of the ISM and the dust. But part of it also comes from the dust and gas distribution on extremely small scales, which we're never, ever going to be able to understand completely. And so that's going to make a difference at some point, and I suppose give you an ultimate limitation on what you're doing here.
I totally agree. And this is part of the reason the spatially resolved modeling is still in the experiment lab, I think, is because
that's going to couple. That's going to, even if you had a perfect, you had no scene whatsoever.
Yeah.
You had a delta function PSF. The ISM is going to couple the radiation coming from different directions in different parts of the galaxy.
At some point, you're running a little radio transfer simulation for every pixel, and even then, you can only marginalize over things you don't know. I agree. There's limitations that we're never going to be able to overcome. This isn't going to solve everything. We can marginalize over things we don't know, and we still need to choose good science questions. We can start getting at that, I think, with some next generation instruments like the local volume mapper. And I think that's going to be enormously valuable. But this isn't magic, and there are hard physical limits that we're going to run into. But we have to build the machinery to be able to ask those questions before we could ever realize what those limits are. I think that's going to be geometry of one of the intractable ones.
So I was wondering how hard it is to train your neural networks accurately when you increase the dimensions significantly, say from 100 to thousands.
Yeah, there's a question of coverage in your training set and efficiency of your training algorithm, and these are both critical questions and ones to be aware of, but they are solvable. LLMs have millions, tens of millions, hundreds of millions of parameters, and this over-parameterization is actually very, very helpful. To be clear, I'm talking about different parameters that live in the network, not parameters that are put into the network. People who are much smarter than me are working on the ability to train these algorithms efficiently, and what we do is rigorously test them against a held out test set before we run them. So I don't know what the answer is for the upper limit of number of parameters. We haven't hit that yet. We've been focusing on, for tens or up to 50 parameters, getting very accurate outputs. But I hope that push that limit soon. And if we can get up to 50 parameters already, we're doing way, 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 way better than any previous attempt. So I would like to run into that problem very soon, but we'll see.
So I love how you ended the talk, because for the whole talk I was waiting. It's like, are you trying to screw in a screw with a hammer with the burstiness problem? Because you can fit a single spectra and not be able to figure out what the star formation history is, because your O and B stars are just going to blast everything else out. So with all this machinery, you're really using the scatter of different distributions, in particular, those tracers that are linked most closely to the short time scale, high mass stars. So I wonder, now after you've done all of this work, are there particular observables? I mean, you can throw the entire SED and it won't tell you anything about the O and B stars. So are there a few distributions of particular parameters, say the H alpha equivalent width, which was used to constrain burstiness 25, 30 years ago, that can actually solve the problem in a shortcut?
Yes, if we do it the hard way, can we kind of figure out a quick and easy way to do it that doesn't take all this machinery? Yep. That's a great question. I think the first thing we're going to do is kick our model around by putting in different models of O and B stars and seeing if we can get a good answer still, or whether we will have one model of burstiness for BPAS and one model of burstiness for MIST. So we're headed in the other direction of more complicated things first. I think the answer will be that with enough objects, we can do it with fewer observables, I guess. You can do it with just H alpha or H alpha plus UV, which is how they classically did it. But that is a question I don't have an answer to, not yet. Yeah, I think we got to do it the hard way first and then ask, was there a shortcut we could have found? Maybe, probably.
All right, let's thank Joel again, and he'll be around.